Yes, ladies and gentlemen, please welcome to the stage your host, Steve Mould! That was me from over there. Hello! Ladies and gentlemen, welcome to Cheltenham's Got Talent, otherwise known as the Overambitious Demo Challenge 2010. Are you excited? Yes! It is exciting, isn't it? It's absolutely brilliant. Let me give you a bit of background to the show. Last year, I did a show with Andrea Sella. We decided that it should be a battle between the two of us, right? It was very badly organised, very badly conceived, but above all, it was lots of fun, right? Now, there was no winner at the end of the show. That's mainly because we forgot to have a vote at the end, right? That's how badly organised it was. Though, after the event, it was generally reported that Andrea had won and that I had lost. Now, I'm not a bit of a person...
I won?
Yes, Andrea obviously has a lot of powerful friends in the media, so I don't know what's going on. But anyway, he is the de facto reigning champion. So this year I said, look, we've got to do it properly, okay? Let's do it properly. It's going to be really well organised, all right? That hasn't happened. It's going to involve 4 of the heavyweight science communicators, right? That hasn't happened either. We've got 3 heavyweights and Andrea Sella, right? We had to let him enter because he's the reigning champion. That's just how it is, all right? So that's what's going to happen. We've got the challenger and we've got 3 awesome science communicators. Does that sound good? Yeah! Fantastic. So I'll tell you a little bit about the structure. There's going to be 4 rounds. Oh, first of all, can I just say a big thank you to UCAS, however you want to, pronounce it. It was UCAS in my day, now it's UCAS, for sponsoring the show. So let me tell you about the structure. There's going to be 2 rounds. The first round, each challenger has 8 minutes, and then there's the quick fire round after that. So that's how it is, and it's going to be voted by clapometer, so you get to vote by clapometer. Don't be fooled by the name. We don't just want clapping, we want whooping and cheering and all that sort of stuff as well, right? So let's test the clapometer. Imagine you've just seen an unbelievable demo and it's time to vote. So I want to know what that's going to sound like on the count of 3. 1, 2, 3. That was really good. Because I was prepared to do that thing, you could do better than that, but actually that was awesome, so we're going to leave it. That's really good. One final thing, one final note actually, and I don't know if this is going to work. If any of you are on Twitter, on your phones, we're going to have live feedback via Twitter and I'm going to monitor it. The hashtag is Demo Challenge, so there you go. If you're not on Twitter, that would have made no sense at all. Okay, I think we're ready to go. Andrea, are you ready to go? Okay, well, as the reigning champion, Andrea gets to go first. So, ladies and gentlemen, please welcome Dr. Andrea Sella.
I don't know why it is that nowadays, seeing a grown man on a street corner or something blowing bubbles is seen as kind of pathetic. I mean, just look at him. He's standing there on his own in a dream. But there was a time when actually blowing bubbles was one of the most respectable scientific trades you could choose. And I'm talking about a time in the 19th century when people began to ask themselves, why is it that if you simply take some water, nothing happens? You could blow until you're blue in the face, you won't get a film, you won't get anything. On the other hand, when you actually get yourself a little bit of soap solution and you adjust the viscosity a bit, then Now, one of the deep insights which has come out from this 19th century research is that actually adults are really bad at it. Children are brilliant, and something happens in the brain development which means that adults just lose that ability. But there are other issues. And the interesting question is, why is it that the properties of water change when you actually dissolve this soapy stuff in the water? What actually happens to the water? How does it alter? And for this, I'd just like you to think. We'll do a thought experiment. And you can imagine, in fact, we might not even do it as a thought experiment. If I find a pipette somewhere, we might be able to do it for real. So give me 1 second as I just reach around here. And somewhere in this box of tricks, we have some pipettes. And if we take a little bit of water and we do this, then these little drops come out. And if you look at these drops, if you were able to look at them fast enough, you'd notice that they were almost spherical. In other words, water, by its very nature, pulls itself together into a shape which has the lowest possible surface area. And this is one of the sort of crucial properties of water, the surface tension by which the water pulls itself into that very nice round shape. And we've all seen those videos. I mean, I'm old enough to have actually watched the astronauts do this stuff, sort of putting drops of water into the capsules of the Apollo space program and then Skylab and so on. And you could actually see these beautiful sort of spheres floating around. But I'd like to look at this a little bit more closely. And what I'm going to show you is what happens to water when you actually put it onto different surfaces. And I'm going to show you something that you're very, very familiar with. And the first thing I'm going to do is I'm going to squirt a little bit of water onto a microscope slide. And you can see it here. You can see me sort of flipping it over. And it's a microscope slide which should have just come out of its box. It's got little bits of fluff on it. We're just going to put a drop of water down. Now you can see that very nice round shape as the water comes out. And we'll put it on. And you can see that the water adopts a nice dome shape. And if we lowered our camera slightly so that we're actually edge on, you can see that the water, crucial thing to look at is the angle that the edge of the water makes to the glass. And you can see that that angle is actually quite obtuse. Fine. What does that mean? It means that the water is actually wetting the glass. And so there's a fight going on between the water wanting to pull itself together into that nice round shape, and on the other hand, the fact that the water wants to talk to the glass. And so there's a battle of the energies between the surface energy of the water that's trying to pull the water into a sphere, and on the other hand, that nice interaction between that glass surface. And glass is silicon dioxide. There's loads of little OH groups that are poking up. And these OH groups are perfect for talking to the water, which of course is HOH. And so you start getting hydrogen bonding and interactions. And so the water wets the glass very nicely. Okay, let's change the surface a little bit. Now what I did yesterday back in London was I took another microscope slide, and onto it I put a solution of something called trimethyl silyl chloride. Doesn't matter what that is really. You can just think of it as little greasy blobs with a reactive bit underneath. And what they'll do is they will go and sit on all those OH groups and cover them up. Let's go and see what the shape of the drop is going to be like. And you can see, I think, the drop perhaps stands up a little bit more proudly than the one before. Not an awful lot, and that may actually be because we've waited 24 hours and the glass has degraded slightly. Okay, so then I went and talked to my friends in Ivan Parkin's research group, and they work on altering the surfaces of glass in strange ways. Now, I've altered the surface of this glass, you can see, with a lot of cotton wool hairs, which may actually screw this all up. Let's see if we can clean it off. But this glass has been treated so that it doesn't simply have little greasy bits. It's actually got long, snaky Teflon bits sticking out. And the Teflon and the water are not going to like each other. And let's just bring our drop down. We'll put it on the surface. And what you should see is something very different indeed. You see these beautiful, almost spherical drops. And if you go and take a look, and I don't have a pointer, but if you think about the angle that drop of water is making to the glass, it's now incredibly acute. And what that's telling you is that there's very little interaction between the glass and the water, whereas the water is holding itself. And if we tip this very slightly, the water will just go eventually running off in beautiful little sliding drops. And this camera isn't very fast. Okay, so now we know something about water and its properties. But now there's the interesting question. What happens if we get, what do you call it? Old school fairy liquid. And there's a certain amount of derision for how old my bottle of fairy liquid is, and we're just going to find out whether it still works. So I'm just going to take a little bit of fairy, and I'm going to come down, and I'm just going to touch it onto the surface. Now, what's going to happen? Well, remember I said you can't blow a bubble without having the soap there? Why is that? Well, the reason is because the liquid is so strongly held, you can't stretch it out into a film without it pulling back. In other words, what you're doing is you're lowering the surface tension, lowering that surface energy by putting the detergent. And the detergent sits on the surface. It's got its head down in the liquid, and it's got one or two tails kicking up in the sky above. And in doing so, it lowers the surface tension. Watch what happens to my drop. Touch it down very delicately. Okay, so we've put a little bit on there. Let's titrate in a little bit more. You see, each time I touch it, it sits down a little bit further. And what we've done is we haven't killed the surface, we've actually killed the liquid. And it's sat down. And so we can play around with these games and change the shapes of liquids. And so this takes me to the bit of the whole talk that isn't going to work. What is my favorite liquid? My favorite liquid has got to be mercury. And some of you may have come last year to my talk, Mercury Window on the Invisible. And what I have here are some Petri dishes. And in the middle of the Petri dish is a drop of mercury, and it's sitting in a solution which has some chromium in it. It's a very fiddly experiment, and every time you jump up and down, the whole thing moves, and it messes it up. But what I'm going to do, I'm going to kneel down very carefully, and I'm going to touch that blue drop of mercury. Let me just move it into the center, because I think it's going to be the one that will do what I want it to do. So here comes the wire, and think about what you're seeing. You're seeing a drop of liquid just like the one we had on that super hydrophobic surface. And now we're going to touch it with a wire. And look, it beats. And what we're able to do, each time the needle touches the drop, what it's doing is it's pumping electrons into the mercury, and it's dropping the surface tension, right? Sorry, it's increasing the surface tension. The drop rounds itself up and goes away from the wire. And then there's a chemical reaction on the surface which lowers the surface tension, and it sits down, spreads out, touches the wire. Electrons feed in, it bounces back. What's really neat about this is that we've generated a chemical automaton. We've created something almost living, right? It's a beating heart. And what we've done using completely inorganic ingredients. There's chromium, I said to you, a bit of sulfuric acid, some mercury, water. With those, we've actually managed to come up with a system which is able to go bump, 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 bump periodically, transform chemistry into mechanics. And it's all using very, very simple things. Gravity, surface tension, a few electrons, and the rate of a chemical reaction. Thank you very much.
Dr. Andreas Seller, ladies and gentlemen. Now, I I did forget to mention, Andrea, if you go over your time in the first section, it eats into your time in the second section.
That's not fair.
Sorry, I forgot to mention that. Well, you're not going to have much time, that's all I'm saying. Ladies and gentlemen, oh, what's happening? Are you up next?
Yeah, he's trying to.
I'm moving out of the way. Oh, okay, we're saving time. Good, very good. Ladies and gentlemen, you've got someone awesome who's going to speak to you now. Please welcome onto the stage the fantastic Maggie Aderin.
With an intro like that, I've got a lot to live up to. Okay, now, when I was invited to do this, I must admit I got terrified, because I know the sort of experiments that Andrea does. And it's usually the sort of experiments, sort of demos that I do, I go out to schools a lot, and sort of demos I do are things like this. So as a rocket scientist, I like to sort of, create rockets. So I usually do something along the lines of this. So this is a bit of vinegar, a bit of baking powder, put them together, lose the cork, I found the cork, put that in. So this is a sort of scale of experiment I usually work on. Nice, simple, very innocent. Thank you. But I realised for this challenge, I had to up my ante. So now what I need to do, oh, my pictures are free. So now what I need to do is I need to sort of go out there, get out there and sort of do a bit more. And so recently, I don't know if people were hearing on the news, there was the Mars 500 programme, which has been done by the European Space Agency. Now, this sounds like a really weird thing to do, because to me it sounds a bit like a soap opera, a sitcom, where you take 6 guys, you shove them in a sort of, effectively the area of a 3-bedroom flat for 17 months, and you see who comes out alive at the end. So it's a bit like Big Brother's gone a bit mad. So this is the experiment they're doing. So based on this, I decided I wanted to do something themed on that. So first of all, I want to talk about rockets. I want to talk about getting out there. Because my retirement plan is one day I want to retire to Mars. And so I want to look at the technology I need to get there. So now, as I say, at schools, I usually do sort of little vinegar rockets like this. But I want to up the ante, and I want to show you sort of another sort of rocket. Now, the real rocket, the big stuff, because I build satellites for a living, and what we do is we we build a satellite that goes up in a rocket, and they usually have solid fuel, and then they have sort of the liquid fuel, the hydrogen and oxygen. So what I wanted to do is I want to create some hydrogen and oxygen, and then explode it. Now, I was going to put this into a rocket, but the problem is the ceilings in here are quite low. And when you put rockets like this together, they often go of the order of 100 foot. So I just didn't have the clearance. So now, and with the help of my husband, because he helped me set this up, what I'm going to do is I'm actually going to create a hydrogen and oxygen. I'll tell you how I'm doing that. So let's get this going. Yeah, you can see, I hope, that this is bubbling up now. And as by the power of magic, this balloon will slowly inflate. Now, I'm getting my hydrogen and oxygen from water, and that's a very important point. Because when we one day, yes, it's getting quite excited now. When I one day land on Mars, I might want to come back home. And we have found water on Mars, and this is so important, because it means that we can actually make rocket fuel. So now, okay, now, but I won't get this too full, because I have sort of a young member of the audience over there, and I don't want to scare her. So what I'm going to do now is I'm going to try and light this. So first of all, let's turn this off. And I've got my match. Yes. This could end very painfully. So, okay, now I've got it on a long stick, because that really helps with this. So I've got it on my long stick, and hopefully... my rocket fuel. But there's more. That is how we sort of harness energy. I mean, an explosion like that would be useless for getting a rocket. But when you take liquid hydrogen, liquid oxygen, you can actually have a controlled burn and actually launch things, overcoming the force of gravity and getting them into space. So let's assume that I've finally made it to Mars. Now, as you can tell, my ancestry come from quite a warm part of the world. My parents actually come from Nigeria. Now, my retirement plan is to go to Mars and sort of probably live out the rest of my days out there. But the problem is, the average temperature on Mars is -50. And I must confess, I don't do cold well. So my idea is one day, if I ever end up on Mars, I want to terraform Mars. I want to make Mars a lot warmer. And there's some properties of the Martian atmosphere that really play to just what I want to do. Because the Martian atmosphere is very thin, but it is mainly carbon dioxide. And so I've got another little experiment set up here to show how one day I might terraform Mars. So I've got 2 bottles here. Now, just 2 ordinary water bottles. Now, one is just sort of normal atmospheric air. Now, the other one is atmospheric air. But what I've been doing is I've been doing my sort of favourite experiment, mixing vinegar with bicarbonate and generating carbon dioxide. I've been pumping that extra carbon dioxide into this bottle. Now, you can see that I've got 2 temperature probes in each of these bottles. And if I come here, now this is... Oh, my screens have gone. Can I get the screens back? Well, trust me, I have 2 temperature probes, one in each of the bottles, and one is currently reading about 25.7, and one is reading about 25.4. Let me just check. Back. So I wasn't lying. Okay. Now, the blue line represents carbon dioxide, and the red line represents the normal atmospheric air. Now, what I want to do is I want to take this and I want to pump more energy into this system. So this is effectively a greenhouse effect. Now, so what I want to do is actually, for Mars, I want to get some solar sails and reflect more solar energy into the Martian atmosphere. And because the Martian atmosphere is so full of carbon dioxide, I should get a runaway greenhouse effect, and I should raise the temperature of the Martian surface. So hopefully this will demonstrate. So I've got a normal atmospheric air, I've got atmospheric air with a bit more carbon dioxide, I'm going to pump some more heat in, and what I want to do is see how this develops. So now this might take too long for me to do it in the timescale we've got here. But if we leave this for a little while, hopefully we should see this developing. And I think you can actually see some movement already. The blue line, although it was above, it is rising more quickly. So we've got 26.4 plays, 25.6. Yeah. So they're both going up, but it's the atmosphere with the carbon dioxide that goes up a lot quicker. So this is my retirement plan. Now, working on a baseline of -50, I'm not actually going to get up to a balmy 25 or 30. But with enough solar sails pumping energy into a carbon dioxide rich atmosphere, I might at least be able to sort of go out and, walk around a bit when I actually retire to Mars one day. So this is my plan. Okay, so that takes me to the first stage of my experiments. What I'm going to come back on in a few minutes, because Andrea overran. If I go shorter, does that mean I get longer later?
Go on then, yeah.
Yes, I like it. I love a plan. Okay, so what I'm going to do is I'm going to stop there. We'll leave this cooking, and we'll come back to it later and we'll see how it's doing. And then for the next stage, what I want to do is talk about, if I'm going to live on Mars and I'm going to raise the temperature so I've terraformed Mars, what I want to talk about next is creating life on Mars. And I think, again in the news, there's been talk about synthetic biology, how we actually create the building, not just the building blocks of life, but life itself. And I want to talk about that in a few minutes. So watch this space. I'll be back.
Mark Miodownik, ladies and gentlemen. Well, next up we have James Soper, but we have to move some tables and stuff around for him. He's very particular about wanting, the stage to move around.
Not being particularly. It's for everybody's safety. Oh, thank you. It's for everybody's safety, including mine.
Great.
So,
okay, you two move back. That's good.
I don't want to smash anything. These amazing experiments, guys. Aren't these experiments amazing? Oh, sorry.
Absolutely awesome, aren't they? Incredible. Listen, when you're voting, have a think about the different criteria, right? So, have you learned something? Was it original? Have you had your minds absolutely blown by a particular idea? Have you felt as if your life was in danger? These are the things that... Right? Does anyone have any ideas for criteria for different things? Yes? Mum won't let me say it. That's a good idea. Well, ladies and gentlemen, I think we're ready. Please welcome onto the stage the fantastic James Soper.
Did you see that? My colleagues, who I think are absolutely amazing, I'm so impressed by all of this, have taken up so much space. I've had to carry my props on in a Tesla's back. But it's okay, it's fine. We can work with a tiny little bit of stage like that. Guys, thank you for coming to the Cheltenham Science Festival and this amazing demo challenge. I am just a primary school teacher. I don't often say I'm just a primary school teacher. I think primary school teachers are some of the best people in the world, but oh my God, yeah, exactly. Oh my God, what a whole load of people to follow. And we've got another amazing doctor coming. I've got a company called Science Shows for Schools. We go into schools, we talk about science, try and make it as fun as possible. So kids, are you having fun? Yeah? Good? Adults, you having fun? Yes! Good stuff. Everybody stand up for me, please. Good. What I'm going to talk about is human bodies, balance, circus, that sort of stuff, and you guys are all brilliant at balancing, but you probably don't realise how you balance, because you learn to balance before you can even speak. Now, you're balancing because you're keeping your centre of mass. Your centre of mass is an imaginary point behind your belly buttons, about halfway inside your bodies. Can you imagine that? It's an imaginary point that gravity acts through. You're keeping that over your base, and as you stand up, your base is the space between your feet. If you all very carefully, and please don't have an accident, if you'll start to lean forwards for me. Oh, that just looks so cool. Exactly, you can only go so far. You feel the weight on your toes, yeah? You can only go so far before your centre of mass is no longer above your base. You start to fall over. Yeah, that's how you balance, right. Put your legs wide apart. Just careful, don't hit anybody else, right, good. You should find it easy, sideways anyway, to keep your balance because you've got a wide base. Yeah, wide base, easy to keep your centre of mass above it. Now try and stand on one leg. Again, be careful. It's much harder, isn't it? And it's so much harder because now, on one leg, your base is really, really small. I think you guys should give yourselves a huge round of applause and then sit down. Absolutely marvellous. I have a juggling club here. Before I became a scientist and then a teacher, I used to work in the circus. This juggling club has a curved base, and obviously it's not going to balance, but we can make it balance if we move the base to keep it underneath the centre of mass. You can try it on your finger. It doesn't matter what you use to move the base. As long as you keep the base underneath the centre of mass, the object. This is easy, yeah, if you understand what you get for showing off. It's easy if you understand the science. I need a volunteer, somebody to come out and try this. Yeah, there's a young lady there, she looks very keen. Give her a little round of applause. She comes up here to help us. Step up carefully. Oh, yes, beautiful. What's your name? Katie. Hold your hand out flat for me, Katie. You're going to balance this juggling club. All you need to do is look at the fattest bit of the club. Look at the fattest bit. Super. Oh, oh, oh. Katie, you're doing brilliantly. Try it on the end of your... Ooh, hang on a minute. Is it fair of me to make you do this in front of all these people and not give you any practice? It's not, is it? I'm going to make it... Yes, I'm just going to make your dad look at it. I'm going to make it a bit easier for you. Hold your hands up like this, everyone. Waft your faces. Oh, that's nice, isn't it? We've got this wonderful atmosphere. You're going to try it again with this thing. It's a peacock feather. Put that on the flat of your hand. Or on the end of your finger, yeah? Look at the very top of the feather. Just keep your hand. That's it. Go forward. Yeah. You're gonna have to. You move your finger underneath it. Come in the middle. You've got a bit more space. The air's gonna catch the fronds of the feather. That's it. Good girl. Well done. Good stuff. The air's gonna catch the fronds of the. Exactly right. Give this lady a huge round of applause. I've got another object we could try and balance. This has got a centre of mass. Funnily enough, the centre of mass isn't actually, it's not a physical place in this. It's actually right in the middle of the ball. See if we can balance this. This is difficult to balance, and I'm good at balancing. We helped that balance because the air was slowing it down. I'm going to help this balance by very simply giving it a spin. Now, spinning things want to stay in the same place. Spinning things, basically, they balance really well. It's gyroscopic stability. As a primary school teacher, feeling the need to use a really big word there because of the other people. Spinning things want to stay in the same place. I need another volunteer, somebody to try this. If I do it, it's a trick. If somebody else does it, it's science. Perhaps a young chap. No, genuinely. The young man at the end, yeah, the back there. Give him a big round of applause. No rush, but get a move on. This is timed. What's your name, sir? Nick, or just Nick? Nick. Stick one finger up in the air for me, Nick. Good choice of finger, Nick. You need to hold this really, really firm, like you're poking someone, yeah? I'm going to spin the ball. I'm going to put it on the end of your finger. Because the ball is spinning, it should stay there. Nick, they are going to clap for as long as the ball stays balanced whilst it's on the end of your finger. Are you ready? That was good. It didn't last too long though, did it? Did you feel your finger getting a bit warm? Yeah, a little bit. That's a force called friction. Rub your hands together, you'll feel that friction, yeah? As the ball's turning on the end of your finger, the ball's heating up, your finger's heating up, the ball slows down, stops balancing, right? This is where the overambitious bit comes in. I've worked out that we've got a machine here that we could try and use to take away some of this friction. Right, this is a hand drill, just a quick safety. Boys and girls, if you've got one of these at home, don't use them. They're designed to make holes in hard objects. You are a soft object. This is safe. I've taken the end off this, but they're not safe to play with normally. I'm going to spin the ball, put it on the end of the drill. This should work because it's going to be spinning. I'm going to hold it like this, and then you're going to grab the drill off me. So you take the drill with your right hand like this, good. Yeah, perfect. And you put a hand here. Keep it all the way down, good. And then you just stay perfectly still, yeah? Excellent, there you go. Right, they're going to clap for as long as the ball stays balanced when you're holding it on the end of the drill. Quick. Excellent, don't move. Stay perfectly still. I've only got 8 minutes, it would last forever. Give him a huge round of applause. Well done, man. Get back to your seat. Right, we need to be just a tiny bit more over-ambitious, so I'm going to finish by doing a bit of showing off, really, a bit of juggling. Bit of, when I worked in the circus, my official job title was manipulator and equilibrist. That's a fancy way of saying juggler and balancer. It was my job to balance things and juggle at the same time. I was going to do some unicycle stuff. Andrea bought his unicycle on. Do you want to see me balance a unicycle? Yeah. This is how people normally do their unicycles and things. Oh, Andrea, you've got long legs. Woo-hoo. But this is the This is the over-ambitious demo. Are you ready? Is that touching the ceiling? Yeah. I can't even see that, it's so dark.
Now pedal it.
Now catch it. You're very kind. What I thought I'd do is I'd finish by introducing a piece of sparkle to the show. Isn't that beautiful? Woo. This was from Primark earlier on. It's £2 if anyone wants to go and get one of these. I plan to take it back after this, so I haven't. I'll take £1.50 for it if anybody wants it. But I thought we'd go a bit of showbiz. I'm going to balance this on my head, not like this, and try and juggle at the same time. Genuinely, this is very, very ambitious, especially with these lights. I'm going to try and go for 10 seconds though. We'll have a big countdown. Obviously, when I'm doing this, I'm not going to be able to look at you. So I'm going to do this, and you guys are going to start a countdown from 10. God, I'm knackered. Breathe. Right, let's have a quick practice. Are you ready?
10, 9.
Right, that's fine. If we get down to 0, what do you think we should do? What would be a good idea? Clap, yes. Clap. Nobody likes a smart ass man. What else? We could clap. We could what? We could cheer, yeah. Anything else? Whistle, yeah. Who said throw their babies up in the air? Swing them around. Don't do any of that. Right, guys, this is my last little demo here. Primark cap on the head. I'll start to juggle. I'll say 10. You guys start. Right, are you ready? Oh, try my nose. Ooh. Now the centre of mass is actually in the middle of the cap somewhere, so you can't look at it, which is why it's going to flick about a bit. Okay, here we go. Oh, I can't see anything. It's funny from down there. Are you ready?
10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
Oh, I just put my foot halfway over the end of the stage. Right? I'm not kidding. I can't see a thing. Guys, thank you so much for watching. I can't wait to come out again. I'm really enjoying watching this. I hope you are too. Ready? Last trick. 3, 2, 1.
Ladies and gentlemen. Right, okay, we need to get this table out, so someone's going to help me here. By the way, we've got some great feedback from Twitter. It's actually happening. And I'll go through that later before the second round. There's some great stuff on Twitter, so we'll see how that goes. Are you ready?
We're ready.
Ladies and gentlemen, please welcome. He's already. Oh no. Okay, look, get off. Great. Oh, let's do it properly. I wonder who he is. Ladies and gentlemen, please welcome on the stage, Mark Miodownik.
Thank you very much. Wow, what a hard 3 acts to follow. I'm going to try my best. Alright, so what have I got here? I'm a material scientist. I spend all my time dealing with solid stuff like this. Although this looks like it's a solid, it actually is a liquid, and I just left it alone for a minute, and it's kind of dripping all over the place. And it's being very annoying. It looks like a bit of a tongue actually now. Doesn't it look? Actually, that's going to be the theme for this evening. Actually, a big tongue. Anyway, alright, now, so who's into the football? I guess no one's into football if you're here tonight, are you? Who hates football? Yeah. Well, for all of you who hate football, and I want to say something. At the beginning of every football World Cup, they make a new ball. They do, and they make a new ball for one reason really, which is to fool the goalkeepers, so there are more goals. And they always change it slightly, and the goalkeepers always go, you'll get, the rest of this few months, you'll get this all the time, oh, the ball moved. Anyway, I was thinking about this, like, what if we were to zoom ahead 100 years, and the World Cup's in space? Okay, and we're playing the World Cup in space, and if you use a normal ball, right, so then it's just going to explode because it's got pressurized air in it, and it's a vacuum in space, and it's going to, right? So what you need is a solid ball. Okay, but you need a ball that when it's kicked, it's going to get damaged by that being, by being kicked because it's a solid ball, and it's not got an air pressure behind it to pop it back like a normal ball has. So you need a ball that's actually liquid, right? Because in space, it'll just assume a spherical composition, and there it will be spinning through space. I know it's not a sphere, but anyway, it's quite tough, this stuff. Anyway, so here's my idea. I'm 100 years before my time, as usual, with lots of things. My mum used to tell me that. And she was encouraging me, I think. And so here's my idea for the new ball for the World Cup in 100 years' time in space. It's going to be made of this liquid. And the only thing that's sort of worrying me about this idea is that there won't be anywhere for the ball to stop. You just kick it, it'll go past the goal, and it'll go on forever. And so we'll have to play with walls around the court, and the ball will bounce off those. But if it's a liquid, it won't splat. And so I've thought it through. I haven't just thought, oh, to be a liquid, is that cool? So I think we need a liquid that bounces. So went back to the lab and picked up silly putty. Have you guys ever seen silly putty? This is the largest piece of silly putty in the UK. It's a liquid, it's a non-Newtonian fluid, but when you hit it very hard, it becomes a solid. It's amazing stuff. And I want to prove to you this bounces. Well, I have to go down here, because when I do it on the stage, it breaks the stage slightly. Okay, so imagine World Cup, then I'm playing, because we've cracked longevity and I've been reconstituted as a bike man. And it comes to me and I chest it down, and it bounces up. Oh yes. Okay. Now, this is going to be an ongoing experiment, because I want to prove to you this is a liquid. I'm going to put it on the edge of there, and you'll see it's going to be like a timer. This is going to melt and drip down the edge of the stage as the whole process goes on. All right, there's a wallet here. Is that yours, Andrea? Yeah. Okay, now, next one. In space, right? We're in space, and well, I'm thinking that the athletes are going to have to practice on Earth, though, probably a lot of the time. Not everyone's going to be able to afford to go in space, despite Maggie's best efforts, I'm thinking. So what we need is a way of levitating people on the Earth, so they can practice weightlessness. And I've got a material just for that, out of the library, of materials in it. It's barium yttrium copper oxide. It doesn't sound very good, does it? And it's a ceramic, and it's pretty unprepossessing. And if you were to make it in the lab, you could do all sorts of tests on this, and you wouldn't be very impressed. And people did do this sort of thing for ages, looking at all these things, and completely went past this material and thought it's useless. It cracks, it's ceramic, it's brittle. Until one day in 1987, someone took the trouble to cool it down with liquid nitrogen. And I'm going to show you what happens when you do that. Where's the liquid nitrogen? Thanks, Andrea. So liquid nitrogen is a liquid that's minus 193, did you say? No, 6, thanks. Oh, that's not a good idea, is it? All right. I'll show you what happens if I do that. It does this. Ooh. Anyway, all right. Now, on to the serious stuff. So here we go. Someone has in Switzerland. It turns out the Swiss are very methodical. We will check it at minus. No, that's Alex. Okay. So they did this experiment. So I'm just putting this liquid nitrogen here, and all I'm doing is cooling it down very, very cold. Now this ceramic doesn't appear to change at all in its visage, and I'm going to show you what this whole experiment is looking like with this camera. Am I? No, I think it's. Is it good? Full screen. And Joe, this is a competition. You shouldn't be helping me. We're in competition. This is the.
He's not helping you.
Can we have this up on the screen or not? Oh, we're flagging through. It looks beautiful. Is it possible?
You'll probably need to plug this cable in.
That cable in. Oh, I see. You pretended to help me. Oh, sabotaging. Where did the dongle go? I wonder where it is.
Oh, the
in your
dongle's
pocket.
missing now.
The dongle! Oh my
Oh,
god!
yes. Sneaky, these chemists. Sneaky. The sneaky ones go into chemistry, the honest, integrity, football-loving ones go into material science. Watch that. All right, now. Is it? Oh, there it is! That's coming up. Okay, now, okay, it looks pretty boring. It looks pretty boring, but it does one thing. It becomes a superconductor, and this means that this material can conduct. Oh, should I put that in there? Well, I could. Anyway, well, thank you. It's pretending to help again. It becomes a superconductor below a particular temperature, which they call warm superconductivity. This is warm superconductivity. Anyway, that's physicists for you. And what that superconductor does means it will conduct electricity at zero resistance. That means if we could make these into wires, we could conduct electricity in this country without any resistance. So we would immediately gain 30% of the electricity we lose by just conducting it around. We lose 30% of the stuff we generate. And as you might imagine, lots of people are very excited. God, I wonder if we can raise the temperature to room temperature. And there are millions of people working on that right now, and no one seems to have got any much further than this. But look at it. Superconductivity does one other thing. It repels magnetic fields. So if I put a magnet on it, and this is quite difficult to get this to work properly, but if I'm not an idiot, I am a bit of an idiot, I can feel it. Ooh. Whoa! There we are. Now, oh! Hold on a minute. I'm just pretending to make this look hard. If I go on the side, there we go. It looks like a planet drifting in space. Now you think I've got strings, don't you? You think I've got strings? What's this? Underneath. This is one of Andrea's pipettes. I'm using his equipment. It might. Oh, God, it's very strong. Anyway, so there we go. Now look, we said over-ambitious demo challenge, and this is quite a big magnet. It's not as big as a football player. Does anyone have any bigger magnets that I can try with this? Anyone? Andrea, the likely suspect. I'm putting a bit more liquid nitrogen on it. We're going to really need to soup up the temperature on this one. All right. Bring forth the magnets with all speed. Oh yes, he's delaying tactics. Bring the whole thing.
I'll give you extra time because Andrea's sabotaging.
He has been. How am I doing for time, by the way?
Not well.
Is this my last demo?
Yeah.
Is it? All right, let me just see. If this is an enormous magnet, which he almost couldn't get off, and he wasn't joking, and I'm not going to put it near that steel because I'm not going to be able to get it off either. Ooh, look. Yeah, that is going to be bad. That's going to be very, very bad. Vengeance is mine.
Andrea having to get a whole new set of credit cards.
All right, here we go. Can you see this? No. Is it there? Okay, here we go. Gosh, all lit. Whoa! Ladies and
done?
I'm done.
Mark Miodownik, ladies and gentlemen! Right. That is the end of the first round. We have not very much time to talk about. I'm going to quickly share some great tweets. Tweets are what they call them on Twitter. It's very complicated. First bubble blowing challenge proving difficult for Andrea. Lovely. Word of the day, super hydrophobic. Lovely, Andrea. Okay, so some stuff there. Mega teacher bonus points for OHT use. Very true. Hydrogen and adaptability from Maggie Adrin. Impressive work. Surely the first event at Cheltenham to get the entire audience to stand on one leg. Nice precision. Classical dynamics. FTW. If you don't know what that stands for, I'm not telling you. How to return items to Primark while maintaining dignity. Good. Show full of firsts for me. Never thought I'd see primary school teachers encouraging a kid to use power tools. There's a very tiny man holding chewing gum on stage. I guess that's a joke. So very good. Right, Andrea. So you're to go first in the quick fire round. Now, would you like to hear how much time you have?
Well, I was told the other day that I have a tendency to be verbose, so I suspect I don't have much.
20 seconds.
All right. Well, I was going to give you a long story, a long spiel about my childhood and my nickname and stuff like that. But let's cut to the chase. I want to talk about catalysis, one of the most important issues in chemistry. And I have here a small piece of platinum, which I'm heating up to red heat. And I'm going to put it into this conical flask, which actually has a bit of hot methanol in it. And when I put it in there, it fell in. That's a bit of a bore. Okay. So we're going to try and relight this. We'll get it back in. We'll get it in there, and I think somebody else should probably get talking because we're running out of time.
Andrea Stella, ladies and gentlemen. Who knows? It might do something. I guess we'll find out. Okay. Maggie, do you need the table back?
Yes.
Great. Okay. Right. So let's be quick here. Okay. Can someone help me with the table?
Leave it where it is.
Oh, great. Leave it where it is. Wonderful. Ladies and gentlemen, Maggie Adrin with extra time.
Okay, so if I could have the screen back on, we can see how my my atmosphere's doing. Oh, lovely, thank you. Oh, Andrea, I want to borrow some of your equipment again. Can I have your blowtorch and also your dry ice? Because as we were talking earlier, oops, I'm sorry, let me get this. Hopefully you see the temperature. Yeah. So carbon dioxide, 40 degrees C, compared with a normal atmospheric air, 33. So that's sort of the order of a very large temperature difference, as you can see. We'll leave it at that. Okay. Now I want to talk. I said earlier that I was going to talk about sort of creating life. Hey, in here. And so what I wanted to do, because I don't know if you heard on the news, the synthetic biology. That synthetic biology was something I was introduced to only about a year ago. Oh no, sorry, that's wrong. Stop! Synthetic biology sounds incredibly exciting, because this is actually creating life. Taking DNA, manipulating it, putting the sort of the right combinations together and creating, so far, things like bacteria and things like that. So what I wanted to do is I actually wanted, I've got to get the right container here. I wanted to actually look at the building blocks of life. And so, yeah, I think that's the one. I go around sniffing containers every so often, because I don't label, oh no, that's the one. And so what I want to do is actually look at the building blocks of life. So first of all, now this is sort of a traditional experiment. I've taken a kiwi fruit, and in the comfort of my own home, I took the kiwi fruit and I mashed it up. And I put a bit of salt with it and a bit of washing up liquid. In fact, I used Fairy 2. Fairy is just amazing stuff, really. So I used Fairy 2, I mashed it up. And what happens is, the Fairy and the salt break down the cell walls of the kiwi fruit. And then... It's got to do that every so often. It breaks down the walls of the kiwi kiwi fruit. And then what I did is I heated it up, and then now I've got the kiwi fruit in solution. So now, if I'm hopefully very lucky, what I've got to have here is isopropanol, which is why it was a bit of a whiff. And I put it in the dry ice to cool it down. And hopefully, if I pour this solution of kiwi fruit now into this dry ice, what I should hopefully get forming on top is the DNA. Now, it's the DNA, it's been mashed up and it's been extracted. Actually, I might have to use your camera, I'll bring it over in a second. But hopefully we should get the DNA precipitating out into the isopropanol. Now, the building blocks of life, creating life seems like an amazing thing to do. And because I heard about synthetic biology about a year ago, I'm going to get you for this. I thought that I ought to experiment myself. I thought that I too wanted to create life. Now, so I sort of started experimenting, and I actually sort of succeeded in what I was trying to do. And I'll show you the results of my experimentation. I have it here. Yes. And then she's dead on cue, she starts crying. So yes, this is creating life. Now, what I was going to do is, I was going to do a live demonstration on the stage about how we created this. But it is before the 9 o'clock watershed, so I don't think I should go there. But Lauren is, this is Lauren, my baby daughter. She is the love of my life. I'm totally besotted. And so, but this was actually creating life. Now, I want to do one more experiment. Now, I think, I can't see the DNA forming. So what I'm going to do is going to take this dry ice out, and I want to do, oh dear, one more experiment. Now this bowl is incredibly cold, so this experiment might go badly wrong. But hey, it is the extreme demo challenge. Now, Andrea, may I use your blowtorch? Because what I want to do, yes. I was talking about rocket fuel earlier, and I wasn't actually going to do this demonstration because it's a tad dangerous. So what I wanted to demonstrate is you can make rocket fuel out of almost anything. Now usually I'd use a galaxy bar for this, but what I'm going to do instead is use this, which is actually dairy milk. Now this is a chronic waste of chocolate, I'm so sorry, but it has to be done in the name of science. So, oh dear, this is going to go horribly wrong, but hey, what the heck. Now, so what I have here, now where is it? Is I have the components of a solid rocket. So this is something called potassium perchlorate. And the nice property about potassium perchlorate is it is a molecule which has 4 oxygen atoms imposed in it. So it just comes as a white powder. Now I do this experiment abroad sometimes, and often I travel with sort of little packets of white powder. I often get looks at the airport. So what I'm going to do is I'm going to put some of this potassium perchlorate, just a little bit, in the very, very icy cold bowl. This is very foolish. It's in the very cold bowl. So this is actually supplying my oxygen, so I'm just going to break that up a bit. Okay, now, what I'd like is actually have, that gets me every time, you think I've got on, don't you? And so what I'm doing is I'm breaking up my chocolate, so my chocolate is actually going to be my fuel, the potassium perchlorate is providing the oxygen, and what I'm going to do is set it on fire, and if this works, what you do is you end up with a beautiful lilac flame. Because the potassium, if you remember your flame test from school, the potassium gives a very sort of violet, sort of a lilac flame, and so we'll see if this actually works. I don't think that's small enough, and I think I'm going to crack my bowl. I'm going to step aside. So here goes. Oh, it's sparking. I'm getting a bit. Go, flight. Oh, dim the lights, thank you. Now, you can see it's actually, well, I think it's unfortunately. Oh yeah, you can see it sparking every so often. But when if it does go, and I think sorry, my bits of chocolate are just too big. What a waste of chocolate! My bits of chocolate are too big. But if it does go, it burns with a really beautiful lilac flame. So I think I'm probably out. Oh, thank you. I'm probably out of time. But yes. DNA, creating life. Hey, you've got more balls than me, haven't you?
2 more, I think.
No, of course, I don't think it's going to go. But effectively, that's the end of my talk. Thank you very much.
Now you gather in, ladies and gentlemen. We're going to clear this table, right? So, no, you're fine. Oh, great. Ladies and gentlemen, James Soper!
I'm I know time's getting on. We can't really go over the ad, can we? Because we've got other stuff happening. Guys, I had a whole series of different stuff. We're going to talk about gravity, we're going to talk about parabolas, and then I was going to juggle eggs up here. But we haven't got time to do it, so I'm just going to do one experiment and let Mark get out here because I want to see him again. He's absolutely superb. If you want to, I'll do the whole egg juggling thing outside afterwards. You can all come and have a look at that. I was inspired by Maggie's demo earlier. Watch really closely, listen really carefully. For that statement, you might just be able to see a reaction. Thank you.
James Soper, ladies and gentlemen. Right, we can leave the table, I think. Well, I will, and we'll see what happens. Where is he? Doesn't matter. Ladies and gentlemen, please welcome and move your legs out the way. Ladies and gentlemen, Mark Miodownik.
I was going to do tongues. This is the countdown. But we're not going to do that yet. Or later. We can come later. Look at this silly putty. It's melting. Who are these keys? Anyway, alright, now, what I'm going to talk to you about is another material that's extraordinary, and it's to solve the problem in space, for some reason, I don't know why, of that thing where you, when you go to the loo, right, has anyone done this? You go to the loo, you go to number 2, and then you hear this plop, but before you were expecting it, and it's a sort of metallic sound, and then you realise your phone is now where it shouldn't be. And in a natural place for a phone. And then you think, oh no, first of all I've got to get it out, and how am I going to do that, and I've got to, and then secondly you think, oh my god, my contract, I've got to go and buy a new phone, because water is going to completely bust the phone. Sometimes it doesn't, but mostly it does completely. That's because water conducts electricity. And it shorts out all sorts of things, and it blows your chip. So what if you had a liquid that didn't conduct electricity in your system, right? Then you would just take that risk out of your life, wouldn't you? That's worthwhile research, isn't it? So we went back to the materials library and we looked for many liquids and we put many phones in many liquids. And the phone companies love us. But finally we found one, and it's called a fluorocarbon liquid. And what I need is a volunteer from the audience to give me their phone. James, why don't you give me your phone? You've been doing some great demos. Sorry. No? No phone? Oh. Andreas, and he's going to give me his phone. My arch rival. Okay, so it works. Has anyone got Andreas' number?
Yeah. I've got it.
Okay, well,
I can give it a call.
Let's see if this is going to completely ruin Andrea's phone.
You going to call Andrea? Do you want the mic?
Yeah. I don't need to say anything. Okay.
You can't have it then.
It's ringing. Is it ringing?
Andrea, I could hear you, but it's in a different medium. What are you saying?
No, it's not. Yes. So it's
Always the saboteur.
Hello, Andrea. Oh. Oh no. Zoe?
Hiya.
Can you hear me? Alright, let's approve that. Just say something.
On speakerphone.
Oh no, hold it. Oh, here. Go on.
Everybody vote for Mark.
It works, guys. The toilet thing is sorted. Who said science doesn't help you? Okay. Mark Miodownik. Right. Quiet, because we've run out of time. I want to tell you two things very quickly. There is Meet the Engineers going on at 8:15 in the, I can't remember where, so go and ask about that. James and Mark have been training these guys up in how to communicate, so go and find out what they're up to. It's a free show, it's completely brilliant. Also, after this, there's a question and answer after this about this stuff, but that will be after we've cleared the stage, so if you want to wait in the talking point, we'll be there to answer questions about what's gone on here. So that's it, it's time
ladies and gentlemen, to vote. Are you ready? Okay, we're just going to go through them one by one, and it's a clapometer. Ladies and gentlemen, first up, let's hear it for Andrea Sella. Let's get Maggie up onto the stage, if she's still there. Yes. Ladies and gentlemen, let's hear it. This might be cheating, but ladies and gentlemen, let's hear it for Maggie Adderin. Ladies and gentlemen, let's get James Soper on the same. Ladies and gentlemen, let's hear it for James Soper. Ladies and gentlemen, the final one, come up on the stage, please. Let's hear it for Mark Miodownik. Okay, it is, ladies and gentlemen, it is a three-way draw. Honestly, I think it might be a four-way draw. It's very, very difficult to say. I don't know, maybe if you've got bits of paper or something, give them, oh, there's no time for a tie break. If you've got bits of paper or something, or give them, maybe vote and write on a piece of paper or something like that, because at the moment I think it's a draw unless anyone's got any obvious... We'll do the tie break. We might be able to do the tie break. Two of you got to go there. Two of us have to go. Well, that's your problem. Ladies and gentlemen, that is it. I'm not prepared to declare a winner because half of you will lynch me. So, ladies and gentlemen, let's hear it for all four scientists.